when we talk about levers, levers are simple machines. All right? When we talk about levers, there's 3 different types of levers. 3 different classes. Class 1, Class 2, and Class 3. And they all have to do with where the load force, where the effort force, and where the fulcrum are on the lever. Those are the 3 parts to any lever. So in a Class 1 lever, okay, in a Class 1 lever, all right, we've got the fulcrum, which is this triangle. Now the fulcrum is going to separate the load force from the effort force. The fulcrum is right smack dab in the middle. Okay, it basically divides both of them. All right, now a Class 1 lever has a mechanical advantage. And when we talk about a mechanical advantage, we're talking about the amount by which a simple machine makes you put in less effort. The greater the numerical mechanical advantage, the less effort you've got to put in. If the mechanical advantage is greater than 1, it's going to take you less effort. If the mechanical advantage is lower than 1, it's actually going to take you more effort to do something using that machine. And I know what you're thinking. You're like, what? You just told us simple machines make our life easier. We got to do less effort. But that's not always the case. And we still use these types of levers anyway. Okay? So a Class 1 lever is identified by having the fulcrum in the middle. The fulcrum will separate the load force from the effort force. Okay, a really good example of that is a seesaw or teeter-totter in a park. Okay, it balances on both sides. Your triple beam balance kind of works along the same lines, where when you take the mass of something, you've got your object on one side and you're adding mass to the other side to try and balance them out. Okay? So when we talk about a Class 1 lever, this is the image that we're actually coming up with. This is the setup that all Class 1 levers are going to have. Okay? Now, here's the deal though. The vast majority of levers are not necessarily Class 1 levers, because this doesn't really lower the amount of effort you've got to put into something. Okay? It doesn't necessarily do that. But other types of levers actually do. Case in point, the second type, which is unfortunately just called Class 2. Class 2 looks a little bit different. Okay, Class 2 still has a bar. And in this case, though, the fulcrum, I'm going to draw the fulcrum in green here, and I'm just going to put an F for fulcrum. The fulcrum is on the end, and the fulcrum is the pivot point of the lever. Okay? The fulcrum is on the end, and in this case, the load is in the middle, and the effort is on the end. All right? This does have a mechanical advantage. And a really good example of a Class 2 lever is a wheelbarrow. Okay? If you think of it this way, you've got your wheel here, right? And then you've got your bucket, and then you've got your handle, and there's a little pivot here. So you can put a lot of stuff in here. You can lift it up and put your effort here. This is your load, and here is your fulcrum. Okay, so a wheelbarrow is a Class 2 lever. And do you remember when we talked about the 5 things that simple machines are able to do? They're able to change the direction of the force, intensify or lower speed. They're able to do a variety of different things. Some machines can only do one of those things. Some can do more than one. Okay? This type of lever actually lets us displace a greater amount of load than we could otherwise. So it does have a high mechanical advantage. Okay? And then we get to the last of the levers, class 3. And this is where, when we talk about machines making your life easier, this is a lie when we talk about class 3 levers. They actually make you do more work. What the what? Okay, we're sitting there and we've got our same bar, okay, or plank. Our fulcrum is still on the end here. But whereas in a class 2 lever, the load was in the middle and the effort was on the end, in a class 3 lever, the effort is in the middle and the load is on the end. And the perfect example of this is a tennis racket. Okay, we talked about Serena Williams playing tennis the other day and how ridiculously fast she can hit a ball and hard she can hit it. And I wouldn't want to be in the way of that ball because it would leave a really big welt and a bruise, right? So if you think about a tennis racket, it's a horrible drawing of a tennis racket, but there you have it. It's my handle. Really, this kind of looks like a snowshoe. Okay, there's my tennis racket. Now, the fulcrum in this case happens to be the person's wrist. Because when you're playing tennis, you're holding on to the racket and the bendy part is your wrist. The racket is an extension of your arm. Okay? So this happens to be the fulcrum where you hold it. The effort gets placed here on the handle where you're holding the racket. And the load happens to be over here where you hit the ball. And here's the thing. The reason that we use inefficient in terms of effort force machines like this is because they give us ridiculously amazing results. Okay? You try hitting a tennis ball with just your open hand instead of a racket, and you will not get the same speed and the same force. Using a class 3 lever makes us use more energy, but man, oh man, the results are way more than what we could have without using that machine. Okay? Think of trying to play golf. All right? You've got professional golfers, men and women, your parents maybe golf, maybe you golf. And you hit a golf ball many hundreds of yards, maybe hopefully like 200, 300 yards away, and that's far. But you try doing that by just throwing the ball with your hand or kicking the ball. That would probably hurt your toe. Okay? Ball's not going to go anywhere near that far. But you use the actual golf club as an extension. It's a lot more work swinging that golf club or swinging that tennis racket, but the results are far greater. Okay, so class 3 levers take a greater amount, and actually I'm going to write this in blue, they take a greater amount of effort, but the rewards are that much better. Okay? Class 2 levers take a lower amount of effort. So they have a high mechanical advantage. Okay? Case in point, a nutcracker. Okay? Or a lobster claw cracker if you've ever eaten lobster claws. All right? If you take these machines and you try to crack open a nut with your bare hands, I don't think you can do it. Maybe you can if the nut's already kind of open and you can just kind of squeeze it, but your hands are going to hurt afterwards. But with the nutcracker, it magnifies the amount of effort you're putting into it, which means it lowers your effort to get the same result. Okay? By making your effort bigger than it is, that increases the mechanical advantage of a machine. When we talk about mechanical advantages, we're talking about the number, the numerical value by which